All right, number 4 from your homework last night. The very first question looks like this. They call it H, and they tell you that each of the coordinates is written as the X coordinate first, then the Y. So, first function is written like this. They tell us that the X coordinate is the age of a child, and the Y coordinate represents the number of siblings. So, if I was to write that, Y is up and down. If you need to remember that, think of it like a yo-yo, goes up and down. So X is age of a child. Age of child. And Y is number of siblings. So, very first coordinate we have 1 and 4. Next one we have 2 and 4. 3 and 3. 4 and 2. We have 4 coordinates. Okay? We're going to draw vertical lines.
It's a function.
Woo. Is it a function?
Yeah.
It's a function because our vertical lines only touch once.
And we're done with the questions, right?
14.
4B.
It should be the easiest.
4B, same idea. They called it K. They're telling you that each of the coordinates, the first value is the X value, the second one is the Y. X is referring to number of households. Y is referring to number of TVs. But what is the most important are the coordinates. So, for the coordinates, first coordinate is 1 and 5. Second coordinate is 1 and 4.
Oh, look at that.
Next coordinate is 2 and 3. And the last coordinate is 3 and 2. So, when we go to draw vertical lines, on the very first pairing, we draw a straight line up and down. We end up touching 2 points. Therefore, this is not a function. Okay, I roughly sketched what number 10 looked like. Okay? For number 10, what they've done, there you go. For number 10, they've represented the X values and the Y values. The X values are not actual numbers. They're using words. So think of it like you were setting up a bar graph, okay? If I could turn this sideways, I would, and we'd get, this is going to be for cat, okay? This will be for elephant, let's say. Human. Mouse. Rabbit. And rat. Okay?
You missed the mouse. Oh, you got
Did I miss anything? No. So, we're representing the X values with names of animals. The Y values are actual numbers, so let's just estimate where they'd be. Cat would be pretty, decently high. Elephant was very low. Humans in between. Mouse has a very, very high heart rate. Rabbit is higher than cat. And rat is higher than rabbit. Okay? So, looking at this, if I were to draw vertical lines through these, does it pass the vertical line test?
Yes.
Okay, so we could say, yes, this is a function. Now, they haven't really told us much about this study. Maybe this is only the resting heart rate for one cat, one elephant, one human, one mouse. Okay? Let's say that that is the case. If they decided to take resting heart rates of different animals, then we're going to end up with several pulse rates for an animal. So let's say they decide to do it for 2 animals. So for 2 cats, and the other one was 182. 2 elephants, maybe the next guy's was 36. In that case, we wouldn't have a function because I have 2 values for cat, and I have 2 values for elephant, which are my X coordinates. But because they've only given us 1 resting heart rate, maybe it's the average, they've only given us 1 pulse rate, not resting heart rate. In terms of plotting this, guys, The x values, you're going to use words. Now, the y values, I didn't give us numbers because it was going to be such a large graph. I had to encompass 27 to 667. So I'd be having to do a very spaced out graph. So I just kind of estimated. If you wanted to be exact, you could have done a graph going up by 20s, 50s, who knows, okay? Yeah, and it doesn't matter what order you do, rabbit, cat, elephant, human, mouse. Those are just your x values, okay? The second part of the question says, if more mammals and their resting pulse rates were included, would the extended table of values be a function? So let's say they decide to use platypus. We're going to stop there because I have no idea. And maybe his heart rate's here. And another one could have been a dog. His heart rate's maybe down here. Okay? Am I still going to be dealing with a function if I only find one pulse rate per animal? Yes. As long as I have one pulse rate per animal, so maybe this is the average, then we're going to be dealing with a function. But if they decide to start using more than one pulse rate per animal, that's when I'm going to run into two coordinates on one vertical line. We're doing lesson 1.2. Today's September 16, 2011. Happy birthday, those guys. Okay, we're going to do comparing rates of first and second differences. So in your textbook, they've given us an example. And they've written down several things. They have speed, reaction distance, braking distance. They have stopping distance also. But we're going to specifically compare speed to braking distance. So the speed of a car compared to its braking distance. And the speed of the car compared to a person's reaction time. Okay? So in the example, they've given us these numbers for our x. 0, 20, 40, 60, 80, 100. We're going to use the exact same speeds for different types of variables. So really, I want you to think of the speed as our x, or our input. Okay? Our speed is our independent variable, and our braking distance is our dependent variable. So in other words, if I'm driving a car, depending on how fast I'm going, that will influence braking speed. If I'm going slower, do you think it'll take longer or shorter to brake?
Longer.
Shorter.
What?
If I'm going faster,
Oh.
will it take longer or shorter to brake?
Shorter.
Longer.
Oh.
Okay?
You said longer.
Yeah. And we're going to discover about reaction time. Okay? So, the braking distance numbers they've given us are 0, 8.33, 16.33. Sorry.
Come on, sir.
Yeah, it takes that long. It takes that many meters to come to a complete stop. Okay? Sorry, I didn't want to call this quadratic and linear. 16.6, 22.2, and 27. Am I missing something? Oh. I just ruined that.
So you got it wrong. Sir, it's 25 for it. Sir, that's not that far.
Yo, 60 is 25, 40 is 16.667.
Yeah, I made a mistake here.
Yeah, 40 is 16.
So we were writing the wrong numbers in. We're going to look under braking distance. We have 0.00, 1.77, 10, 15.96, 28.38, and 44.35. Under reaction time, I have 0, 8.33, 16.67, 25, 33.33, and 41.67. Okay, so this is what is important for what we're doing right now. We need to figure out if these relationships, technically each of these could be written as a coordinate, okay? And we can plot these all on a graph. It could take us a while to make the graph. It'll be a tough graph, especially to graph 1.77, 15.96. It'll be very hard to plot on a graph. And what question they're going to ask us is what type of relationship is there between speed and braking distance and speed and reaction time. We want to figure out if there's a linear relationship or a quadratic relationship. In order to do these, we're going to find the differences between the y coordinates. So as long as our x coordinates are consistent, so if you notice they're always going up by 20, same with this one here. So because they're consistent, I can compare my y coordinates. I'm going to find the difference between each of the y coordinates. So for the what we'll actually do is we'll do speed and reaction time first. Okay? And I'm going to subtract 8.33 from 0. This is going to be called the first difference. Close to that. So, what is 8.33 subtract 0? Good. What is 16.67 subtract 8.33?
8.64.
Okay. The next difference we're looking at is between 25 and 16.6. So I take the number 25 and I subtract 16.67. It turns out to be approximately 8.33. Again, we take 33.33 from 25.
8.64.
8.63. And again, we're going to end up with 8.33. So all I did there is I took this number and subtracted the number above it. Okay? In all of the differences between these numbers, we ended up with the same value. Okay, for braking distance, we're going to find the difference between the numbers. The very first one is 1.77.
Next one is 5.33.
5.33.
Next one is 8.86. 12.42.
And 15.97.
50, yeah, 50.
What's that?
12.42. Okay, so when I found the first differences here, it turns out none of these were the same. I got a different value for every single one. So because I got a different value for all of these, we know that we do not have a linear relationship. If the first differences are not the same, we're going to take it a step farther. We're going to find what's called second differences. What we're doing is testing to see if this is quadratic. If the second differences are the same, then we have something that's quadratic. So, difference between these two,
3.57.
these two are 3.56, and 3.55. So, when we look at our second differences, and that is this number, subtract the number above it.
It's actually 3.5, yeah.
Our differences are approximately the same. So, because our differences are approximately the same, that means we have a quadratic function, or if you guys remember, that's what a parabola is. We're dealing with quadratic, okay?
So you always have to do the second differences or figure out.
Yes, so if the first differences are the same, then we already know it's linear. We don't have to find the second differences. If the first differences are not the same, we take it a step farther and look for second differences. If the second differences are not the same, that means it's neither quadratic nor linear. Can't go forever. After that, we can't prove anything. There's no real constant relationship there. Now that we figured out how to tell if something is quadratic or linear by looking at the differences, we're going to do the same with looking at a function. So if you guys notice, I have a new symbol in front of these. You guys haven't, or most likely haven't seen this before. F of x means the function with the variable x. So we were discovering what functions are. What I'm telling you is this equation is a function. So is this equation. It also has the variable x inside of it. When we go to graph, I can simply replace f at x with y, and it really means the exact same thing, okay? But we're going to get used to writing things in function form, because as you get higher in math, it becomes easier to deal with than just a second variable. So, what's important right now is we're trying to figure out, again, if something is quadratic or linear. In order to do that, I'm going to have to look at the variable in the function, and this function, f, tells me that the variable is x. So I look at the x in the function, and I look at the exponent specifically. What exponent is this x to?
1.
1. Even though there's not a number there, it's assumed that's to the exponent 1. If something, or if the highest degree the equation, so this is the highest degree because there's no other variables. If the highest degree is 1 in an equation, that means it is a linear equation. Automatically.
Wait, what was that?
So if the highest exponent in a function, and I mean exponent of a variable, is 1, that means we have a linear relationship. So when we graph it, it'll be a straight line. In the second function, the function is f, so we're talking about this equation. The variable is x. So we look at the variable on x. If the highest exponent is 2, then we have a quadratic function. Okay? Okay, so if we have this function here, I can look at it, and I actually need to simplify this. I can't look at a function and instantly know if it's going to be linear or quadratic. I need to keep it in its simplest form in order to make an assumption about it. So I'm going to collect our like terms, which are 3x and 2x, and 3 and negative 4. I'm going to get just x, or 1x if you like, minus 1. Now that this is simplified, I know the exponent is 1. And if the exponent was 1, what kind of relationship do I have? Linear. Okay, again, I have another function. Now we looked at the first one and it looked like it was going to be linear because we're all to the exponent of 1. When I start off, this x is to the exponent of 1, and so is this one. But again, I have to simplify this, so I'm going to distribute my x's. I'm going to end up with x squared plus 3x. Now there's a problem. I have x squared and I have x to the power of 1.
It's quadratic.
Why would this be quadratic?
No, it's not quadratic because you added, right?
Because you go with the highest exponent.
Yes, so even if I have a power of 1, I go to the exponent with the highest, I go to the variable with the highest exponent to tell if it's linear or quadratic. So even though there is a variable with the exponent 1, because there's also a variable with the exponent 2, I use the 2 to tell if it's quadratic or linear. So because there is an exponent to the power of 2, I know this will be a quadratic.
But if it's higher than 2, it's 1.
And ready? Now on this one, I got to distribute. Remember, I have to simplify in order to figure out. So x squared times x squared is x to the power of 4. X squared minus 4 is negative.
That's neither, right?
Negative x to the power of 2. So I have an x to the power of 2, but I have to go to the highest exponent. This is x to the power of 4. So this is neither or neither linear or quadratic.